Alright, so as you saw, today we're talking about horizontal launches in projectile motion. And what I mean by projectile motion is that the only force acting on the object is gravity. We're going to ignore any air resistance or any other drag forces. And we've already tossed the thing or launched it, and now the only force acting on it is gravity. Like last time when we went outside and launched the baseballs, right? And that's connected to your F3M. The F3M today, I talked about how if we're at the top of a 20-meter building, and we toss the ball 45 meters per second horizontally, the F3M said, how long does it take to hit the ground? And as Stephen pointed out, we know that the time that that ball takes to hit the ground is going to be the same as if we just dropped it straight down. And so we can say, I know the distance it fell. I know that vertically, I know that vertically its initial velocity was what? 0. So now I just have to deal with the vertical acceleration. I know that time then, just doing algebra, is the square root of 2 times delta y over a. So that's the square root of 2 times 20 over 10. So it takes 2 seconds to hit the ground, right? Which is exactly what it would take if I just dropped it. It's how long it would take if I launched it at 90 meters per second. So what's the difference between dropping it and launching it at 45 meters per second horizontally? How far it goes horizontally, right? So the follow-up question that I would have asked, and I'm going to ask from now on, is how far away does that ball land if we launched it at 45 meters per second? And how am I going to do that? Well, I'm going to use the same equation, but now I'm talking horizontal distance, right? So I'm going to say delta x equals the horizontal velocity times time plus 1/2 the horizontal acceleration times time squared. Is that arranged the way I want it to be able to find how far away from the building it lands? Yes. So now I just have to substitute. What was the initial velocity in the horizontal direction? 45, right? Because all of that velocity was horizontal. So that's 45 meters per second times 2 seconds plus what was the horizontal acceleration? It is the same as dropping it. In both cases, what is the acceleration? Well, let's do this. Draw me a force diagram of this ball when it's dropped. Right? If I draw the ball right here, in the dropped case, what does the force diagram look like? Sketch it real quick. Just gravity pulling down, that's it. Okay, in the absence of air resistance, that's it, right? Just gravity pulling down. But what about in the launched case? When the ball's right here, what does the force diagram look like? Gravity Is momentum a force? Nothing else. There's no other forces acting on it. Now you say, but wait a minute, Steve, it's moving to the right. Exactly, because that's what it wants to do. I've said it over and over again. You still don't believe Newton's first law. I told you it's going to be hard to get this. Okay? The fact that it's moving to the right means it wants to continue moving to the right. What force is moving it to the right? None. There's no force required to keep it moving to the right because it wants to continue doing what it's already doing, which in the case of the horizontal direction is to keep right on moving at 45 meters per second. So right here, how fast is it going horizontally? .45 meters per second. How fast is it moving to the right here? 45. How fast is it moving to the right here? 45. So the horizontal acceleration is 0 because there's no force acting horizontally. So this is 0. And so it's just 45 times 2, which is, so how far away does it land? 90 meters. Now, does the vertical velocity of the ball change? Is there a vertical acceleration? Yes. So does the vertical velocity change? Yes. The horizontal doesn't change, but the vertical does. Okay? Which is why it does matter. Not which is why it does matter, but does it matter what speed we launch it at if we're worried about how far it goes horizontally? Yes. But we're not worried about what it doesn't affect is how long it takes to fall. Alright? So try this one on your own, please. I'm on a, we'll make it a 45-meter tower. Actually, we'll do one more together, and then I'll make you do one by yourself. Alright. I'm going to launch at 20 meters per second. We're just going to switch the numbers here. Horizontally. You may have seen me in the last example do this, but now I'm going to explicitly tell you 3 steps that I want you to do. First step is always draw. Sketch what's actually happening in the problem. Second step. Find the time it's in the air. Which is going to be based on which direction? Horizontal or vertical? Vertical, always. And then the third step is we're going to find that distance, or sometimes I'll have you work it backwards and find the speed. But we're going to find the horizontal component. Alright? So back to this problem. We want to know how far away will this give me an animal. What? Chipmunk. If it's launched 20 meters per second off of a 45-meter high tower. I know, what kind of weird, sick person would do that? Right. So step one is to draw a sketch of what's happening in the problem. I've drawn how high the tower is, and I've shown that it's clearly going to be launched horizontally, so that's going to be important. So, step one, done. Step two, find the time it's in the air. It's only dependent on what? The vertical, which in this case I've been given a height that's vertical. And so that's what I'm going to use to find the time. So I know that vertically the distance is the initial vertical velocity times time plus 1/2 the vertical acceleration times time squared. The initial vertical velocity was 0 because all of this velocity is horizontal. There's not any part of it that's vertical. And so now I can solve for t. Again, just algebra. And I get 2 times 45 divided by 10, square root of that. Who? Okay, you want me to do it in slow motion? Right, here's the algebra in slow motion. Delta y is 1/2 a2 squared, right? So multiply both sides by 2. Divide both sides by a. And then take the square root of both sides. Exactly. Since a, for all the projectile motion problems that we do, is going to be 10, then yeah, it's like y over 5. And as long as you know where that came from, I don't mind you using that as a shortcut. The time it takes to fall is the square root of y over 5. So we found the time in the air, 3 seconds. Check. Now, step 3, find out how far it goes. Again, same formula, just now we're looking at it horizontally. Is anything 0? Yeah, the acceleration in the x direction is 0 because there's no acceleration in the x direction because constant velocity, and what's causing it to stay constant velocity and there be no acceleration is there's not any forces in the x direction. And the y forces, right, the forces in the vertical direction are independent of this x horizontal direction motion. Okay? So now then I just take the initial the initial horizontal velocity was 20 meters per second, and I multiply that by the 3 seconds that it's in the air, and I find that it lands 60 meters away from the base of the building. Yeah, this is a little easier, right? We're going to wait until next time to mess with that. Alright? Okay, this one I do want you to do by yourself. Yes, ma'am. What's that? Good. Horizontal velocity. What's that? Vertical height. Good. And I'm looking for horizontal distance. And is there anything else implied? The acceleration in the y direction is 10 meters per second squared. Good. So now I'm going to draw a picture. I'm going to sketch it. It's 29 meters high. It's going 18 meters per second horizontally. Now I'm going to find the time from the vertical. I know that initial vertical velocity times time plus 1/2 vertical acceleration times time squared. And since horizontal launches have an initial velocity in the vertical direction of 0, that goes away. And then again, by algebra, I know that square root of 2 times delta y over a is the time, which is 2.4 seconds, right? If we do 2 times 29 divided by 10, square root of that. Then I'm ready to find the horizontal distance, which is equal to the horizontal velocity times time plus 1/2 the horizontal acceleration times time squared. Are either of those terms 0? Yeah, there's no acceleration in the horizontal direction, so that goes away, and so it just becomes the vertical velocity, which is 18 meters per second, times the time we just found, 2.4 seconds, and that gives me my 43 meters away. Es tan fácil, ¿no? Sí, claro que sí. Okay. Now let's do this. Let's say a motorcycle rides off of a 4-meter high roof into a pool. I got it. Registered trademark. Sorry. If the bike lands, we'll say 21 meters from the base of the building. How fast was it going? How fast was it going when it left the top of the building? When it left the roof? And you can assume, if I haven't told you any otherwise, that there aren't any ramps or anything up on the top of the roof to make it launch non-horizontally. Alright, so we're going to go through the same process. What's that?
Delta y.
That's delta y. What's that? Delta x. And we're looking for speed in the horizontal direction, right? And so yes, so is there any information that's implied that I'm going to need? Acceleration is 10 meters per second squared. Alright, and so I have to find what to get there? Time. So I'm going to do step 1, I'm going to sketch. It's a 4-meter roof. I don't know how fast it's going some v, but I know that it ends up landing over here 21 meters away. There's my sketch. Now I'm going to use the vertical to find the time. Vertical distance is initial vertical velocity times time plus 1/2 the vertical acceleration times time squared. The vertical velocity initially was 0, right, because there wasn't a ramp or anything. So I can use this to find the time is square rooted to A, which is 0.9 seconds. So far, nothing different than what we've done. But then I'm trying to find a speed when I have a distance. I still use the same relationship, right? I know that delta x is the initial vertical velocity times time plus 1/2 the, horizontal velocity plus 1/2 the horizontal acceleration times the time squared. Any of those terms go to 0? Yeah, again, there's no acceleration because there's no force in the x direction. So if I'm looking for the initial vertical horizontal velocity, I know that's equal to the horizontal distance divided by the time in the air. The horizontal distance is 21. The time, meters, the time is 0.9 seconds. Therefore, it must have been going 23 meters per second. Alright. One more. It's the granddaddy of all horizontal launches. Give me a food product.
Banana.
Ramen. That's just wrong. Oh, okay, the cereal. Give me a number.
So hungry.
15.
Yeah, I need a structure.
Okay.
Flagpole. Thank you. That's good. Uh-huh. Yeah. Who? Yep. Give me a number.
57.
Oops, sorry, I should have said it's thrown 15 meters per second horizontally. Right now, we know that because we haven't learned non-horizontal, but eventually that'll matter.
Oh my god.
You got this. All right.
Oh wait, I got this.
Okay, we'll do it quietly then. This is that. We're doing it quietly so that Brooke can finish. And this is that. And I know that that is this. So I'm ready to start. So the first thing I'm going to do is draw this. And then now I would normally say that I want to... Okay. I would normally find time based on the vertical, but this is the one exception. I'm still going to find time next, but how am I going to do it? I know the horizontal distance, and I know the vertical velocity initially. So I'm going to start with this guy. I'm going to start with the horizontal. That's 0, therefore time is the horizontal distance divided by the horizontal velocity, which is 57 over 15. Gives me, what was it, 3.8 seconds? And now I use the vertical to find out how high it is, because I know the initial vertical velocity times time plus 1/2 the vertical acceleration times time squared gives me the vertical distance. Well, it started out vertically going 0, so that goes away, and so it's just 1/2 of 10 times 3.8 squared, and that's that 72 meters that everybody's been talking about. Good work. Yes, because I'm launching it horizontally, there's no vertical velocity, and so the vertically it's the same as if I just dropped it. Because vertically, that, and that are all the exact same vertically.